Okay, today in chemistry we're going to work on using the orbital notation method and electron configuration notation to assign electrons areas that they're going to be located. So orbital notation is probably the most cumbersome, but it's really helpful like when you're assigning quantum numbers. So it shows electrons filling orbitals. You can either use a circle or a line to represent your orbital. I would use a line because it's just easier to draw. When orbitals contain one electron, the orbital will get one arrow, so the arrow is going to represent the electron. A second arrow pointing in the opposite direction indicates the second electron in that orbital. And so we would say that they are paired. Okay, so I've listed your elements from hydrogen to neon, and then you might want to put a pause for a second, and then you need to list your orbitals across the top. So there's going to be one s, and then a 2s, and then remember there are three different p's, so it's 2px, 2py, 2pz. Then you have 3s, and then 3px, 3py, 3pc, and then 4s. And obviously it would go on, but we would never go past 4s. Okay, so then we're going to draw a line to represent an orbital. So I've already drawn my lines to save time. So hydrogen has the atomic number of 1, so that means it has one proton, one electron. So that one electron will go in the first energy level in the s sublevel. So by convention, we always do our arrow going up first. So that represents hydrogen's one electron. It's in the first energy level in the s sublevel. Helium has the atomic number of 2, and so that means it has 2 electrons, and so you will put one electron in the first energy level of s sublevel, and then before we go to the second energy level, we have to fill the first one up, so you put it second energy level in the same orbital, but the arrow going down to minimize repulsion. Lithium, if you look at your periodic table, lithium has 3 for the atomic number, so therefore it has 3 electrons. So the first 2 electrons will be placed in the first energy level in the s sublevel, and then its third electron will now move into the second energy level in the s. Okay. Beryllium has 4 electrons, so the first 2 electrons will go in the first energy level in the s sublevel, and then the next 2 electrons will go in the second energy level in the s sublevel. Okay, and you can count your arrows 1, 2, 3, 4. Those represent your electrons. It should equal the atomic number. Boron has 5 for its atomic number, so it has 5 electrons. So the first 2 electrons will enter the first energy level in the s sublevel. The next 2 will enter the second energy level in the s sublevel. So you have to fill up the s. Remember, you have to fill 2s before you go into 2p, and then it has 1 electron in the p. Now let me give you a word of caution. You will not pair up another electron in this orbital until we have given each of your p's 1, okay, because they are equal energy. Okay, carbon has 6 electrons, so you put the first 2 electrons in the first energy level in the s sublevel. The next 2 electrons enter the second energy level in the s sublevel. And now you have 2 more electrons. They will go in your p, so you'll put 1 in the 2px and then 1 in the 2py. Okay, if you want to put me on pause for a minute, and let's see if you can go on through neon. Okay, so for nitrogen has the atomic number of 7. So you put the first 2 electrons in the 1s, the next 2 in the 2s, and then each of your p's get 1. Now, with oxygen, we can come back and start pairing up. Okay, oxygen has 8, so the first 2 electrons go in the 1s. The second 2 electrons go in the 2s. Give each of your p's 1, and now come back and pair up. Fluorine has 9 electrons, so you put 2 in the 1s, and 2 go in the 2s. Give each of your p's 1, and then start pairing your p's back up. When you get to neon, it's going to have 10 electrons. You should have 2 in the 1s, 2 in the 2s. Once again, give each of your p's 1, and then come back and pair up. Okay. Now, If you'll remember, neon is in the noble gases. It has 8 valence electrons. And so these here in the second energy level, that is your outermost energy level. It is full. It has 8, 2, 4, 6, 8. Okay. Lithium and hydrogen are both in the 1A column, and they both have 1 electron in their outer shell. And you could do the same for beryllium. Well, we don't have somebody to compare beryllium to. Okay, so orbital notation is good, but it takes a little bit more time. So the next way you can do it is something called electron configuration. Now, electron configuration is just going to put up to 6 in the P, and then we move on to the S, but you won't break them up into orbitals. So it eliminates circles and arrows. Instead, the number of electrons in the sublevel is shown by adding superscripts to the sublevel designation. Okay? And let's go ahead and go down here and fill this in. When you add up your superscripts, it must equal the atomic number. Because remember, atomic number tells you number of protons, but if you know the number of protons, you also know the number of electrons. Okay, so we already know hydrogen has 1 electron. Okay? And so that electron is going to go in the first energy level, in the S sublevel, excuse me, and the superscript 1 represents that electron. So we say hydrogen's electron configuration or notation is 1s1. Helium has 2 electrons, so they're going to both go in the first energy level, in the S sublevel, and it contains 2 electrons. So you would say 1s2. Lithium has 3 electrons, so you say the first 2 go in the first energy level and the S sublevel. Remember, S only holds 2, so now you have to move to the second energy level in the S sublevel, and it has 1. So once again, add up your superscripts. It should equal the atomic number, which is also equal to the number of electrons. Beryllium has 4, so you should say 1s2, 2s2. So this simply means that you have 2 electrons in the first energy level in the S sublevel, 2 electrons in the second energy level in the S sublevel. Boron has 5. So remember, S only holds 2, so you say 1s2, 2s2, 2p1. So we're not going to say px, py, pz. We're going to go up to 6 for your p's. Carbon would be 1s2, 2s2, 2p2. 2, 4, 6 equals the atomic number. So put me on pause for a second and let's see if you can do through neon. Okay, so hopefully nitrogen, you said 1s2, 2s2, 2p3. Oxygen, 1s2, 2s2, 2p4. Fluorine, 1s2, 2s2, 2p5. And the neon, 1s2, 2s2, 2p6. So you add 6 plus 2 plus 2, that gives you 10, which is equal to the atomic number. Your highest occupied energy level is 2. And so if I said how many electrons do you have in the highest occupied energy level, you would say 8 electrons. So once again, neon has 8 electrons in its outer shell. This is its outer shell or its outer energy level. It has 8 electrons. Here you could say that lithium has, how many paired electrons does it have? It has 2. And then how many unpaired? It has 1. Okay. All right. So that is electron configuration. Now, the next thing I want to do is show you how to just use your table. Okay. So if I were you, to make this simple, I would take a color and I would outline the first 2 families in a certain color. And for our purposes of what we're doing, you're going to put helium in the same color because helium is going to fit over here for this. And we're going to call this our S block. So if you want to write S block in there, you can. And if you need to write this above here until you get used to it, this would be like S1, S2. Okay? Now, if you'll remember, there are 3 different p orbitals, and they will hold 6 electrons. So you have 1, 2, 3, 4, 5, 6. And so you're going to outline this here. And we're going to call this our P block. Okay? And if you need to, above here, you can put P1, P2, P3, P4, P5, P6. Okay? Next, if you will recall, there are 5 different Ds, and they hold 10 electrons, and so you can count here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is going to be our D block. It's not going to show up very well. D block. And so if you want to, you can put D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. Okay? And then there were 7 different Fs. They each hold 2 electrons. That gives you 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so this is going to be our F block. I don't have another color, so I'm just going to outline it in purple. I'm going to call this my F block. And if you need a number, F1, 2, 3, 4, 5, on through. Okay? Okay, so if you're just looking at your table, you can do this. So if I say to you, hydrogen, give me hydrogen's electron configuration. This is your energy level. So this is your first energy level, second, third. So you'd say it's in the first energy level, and this is your S block. So you'd say 1s1. If I said helium, you bring helium over here. So you would say its electrons are both in the first energy level, S sub level. So you'd say 1s2. For lithium, you always have to start at your first energy level. So you would say lithium's electron configuration is 1s2, 2s1. Beryllium's 1s2, 2s2. Boron, so your S and your P are always going to be the same number. So you'd say 1s2, 2s2, 2p1. Carbon, 1s2, 2s2, 2p2. Nitrogen, 1s2, 2s2, 2p1, 2, 3, 2p3. Oxygen, 1s2, 2s2, 2p4. Fluorine, 1s2, 2s2, 2p5. And then neon, 1s2, 2s2, 2p6. Okay, so let's skip ahead and let's do magnesium. So we're going to skip sodium. 1s2, 2s2, 2p6, 3s2. So we're going to skip around and just choose different elements. So let's do phosphorus. So you'd say 1s2, 2s2, 2p6, 3s2, 3p3. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. Argon, 1s2, 2s2, 2p6, 3s2, 3p6. So that's saying of argon's electrons, you've got them in 3 different energy levels. Okay, so let's do calcium. So you have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay? Now remember a second ago when we did this, so you feel the first energy level first, then your second S, then after 2s, 2p, then after 2p, 3s, after 3p, 4s, and then after 4s, 3d. Okay? So whenever you go to the D block will always be 1 less than the main energy level. So if you want to write in here, we could call this, so if this is 4, you're going to call this 3D. And if this is 5, this is going to be 4D. And then if this is 6, this is going to be 5D, okay? And also look here, after, we're going back and forth, but after 7s, after you put electrons in 7s, you're going to go down and fill your 4f, and notice your 4f, excuse me, after 6s, you're going to fill your 4f. Notice your f is 2 less than your s. So 6s, then 4f, and then 7s, 5f. So when we go down here and we start pulling electrons from this, then we would call this, if this is 6s, this is going to be 4f. And if this is 7s, this is 5f. Okay, so whenever we do this, when we get down in here, after you do 56, notice this is 57. So this actually fits right here, but the table would be too long. So after you do 6s, then you would do 4f, and then if we had to come back up, it would be back up to 5d, and then on to 6p. So keep in mind that your s, your p are always the same energy level. Okay, so let's do vanadium. So it's element 23, okay? So you have to start with 1. So you say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, remember you drop down 1, 3d, 1, 2, 3, 3d3. Okay? Let's do zinc. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Let's skip to bromine. Okay? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, 1, 2, 3, 4, 5, 4p, 5. Okay? Okay, let's do barium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Okay? And let's go ahead and do mercury, okay? And then we're going to go on to Lewis dot and noble gas configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. We have to come down and pick this up. And if this is 6s, this is 4f14. And then you would say 5d10. Okay? Okay, hopefully you can kind of get the gist of what's going on there. And so now we have to talk about some atoms do not fill the predicted order. Okay, so you have chromium, you have copper, and you have silver. Put this on pause and see if you can write in their expected electron configuration. Okay, so hopefully for chromium, you said 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Okay, here's what happens. With the D block, if you have chromium, the D is almost half full. So we're shy 1 electron to be half full. So it's more energetically favorable for the D block to be either half full or full. And so what happens is an S electron will move from the S orbital to the D. And so it should chromium's actual will be 1s2, 2s2, 2p6, 3s2, 3p6. Remember, one of your S's moves, so it's 4s1, 3d5. So you want your D half full or full, and you can do so by pulling from an S, okay? Now let's go through. So put me on pause and see if you can't do copper and silver's actual. Okay, so copper, you should have said it is expected is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. So if we could have one more electron, our D would be full, so it's going to move from the S. So its actual is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Silver, you would expect it to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d9. So once again, we only need one more to fill up our D, so it moves from the S, so its actual is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1, 4d10. So one of your S's moves over. Okay. Now, there's another type of notation called noble gas notation, and it is a shorthand method to writing electron configuration. So for instance, let's say I ask you to do the noble gas notation for chlorine. So you go and you find the noble gas that is in front of chlorine. So you have to go backwards and you hit neon. So you would say for chlorine, it's noble gas notation. So you would put neon in brackets. It needs to be brackets, not a parentheses. And then, so it's saying, when you put this in brackets, it's saying it's identical to neon, and then you pick up from there. So then you'll say 3s2, and then 3d5. Okay? So let's say I ask you to do 10s, SN, element 50. So you go to the noble gas that precedes it. So you're going to go all the way back to krypton. So we say that 10s is going to be exactly like krypton, and then we're going to pick up from there. So then after krypton, you would say 5s2, 4d10, and then 5p2. Okay? So you go to the noble gas that is in front of it, put that in brackets, and then you pick up from that noble gas. You would not put the noble gas in brackets and then start from energy level 1. Okay? Now, our last thing to talk about in this for this lesson is called electron dot or Lewis dot representation. You will use dots in the element symbol, and the element symbol must be written correctly. The dots will represent the valence electrons, or the electrons in the outermost shell, and these are going to be from the S and P sublevels. These electrons are important since they are involved when chemical bonds are formed. So it's an important concept, and we're going to come back to this in the chapter when we get to bonding and formula writing. Valence electrons will determine the chemical properties of an element. I typically only use electron dot for representative elements. Those elements in the last column, so remember these in the last column are called noble gases. They will have 8 valence electrons, with the exception of helium. Since it only has 2, it's going to have 2, and thus they're stable. And so we call that the octet rule. So for instance, if I say, let's do lithium, and the other day on your table, you should have written your valence electrons. So like 1A, this whole family has 1 valence electron. This family has 2 valence electrons. Skip over to 13 or 3A, that's 3 valence electrons. 4A is 4 valence electrons. 5A is 5 valence electrons. 6 valence electrons for 6A. 7 valence electrons for 7A, and then 8A is 8 valence electrons except for helium. Okay? So if I say give the Lewis dot or electron dot for potassium, you write potassium symbol K, you will give it 1 dot. Doesn't matter if you put it here, 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 here. Let's say instead I ask you to do beryllium. So beryllium, we're going to give it 2 dots. And we're just going to go ahead and separate them. Okay. Let's do carbon. Carbon has 4. So you will give 4 individual before you pair up. Oxygen. Oxygen would have 6. So you would do 1, 2, 3, 4, and then pair up. Make sure you can see that you have pairs. And then let's do fluorine would have 7. 1, 2, 3, 4, 5, 6, 7. And then neon would have 8. 1, 2, 3, 4, 5, 6, 7, 8. So that is electron dot or Lewis dot. Thank you.